Okay, this is going to be a video where I explain how many VRs in plus 0 you're going to be getting. There's a very simple answer that basically, like, it's very simple to understand. I'm also going to be proving this in this video later, so if you're a theory maxer, just stick to the end. Otherwise, just when I start the proof, you can leave. But the first part you should be able to understand it. So just say we have. Also, I'm not going to be mentioning about VRs in plus 1 because it's actually the answer is much more complicated. I don't think it's also as useful. Also, before actually going into the details, why would be interesting? How many VRs in plus 0 there are? Basically, to know if you missed one, because that can happen if you have high QT counts. Basically, only with 5, but yeah. So let's say you have a skeleton like this. Okay. Okay, and a goal number of -1. Now, I'm assuming that there are no segments which are equal to 0. This is a simplifying assumption, but really having segments equal to 0 is not a complication, because whether you pick there or not, it doesn't really affect the sum of the segments, right? Which means you actually just get a factor of 2 from there. So you can just work out how many VRs in plus 0 there are, like just pretending there is one fewer segment. Similar thing holds if you have a blocky fish. We know from last time that blocky fish can be replaced for free by picking a segment or not. So that's a factor of 2. You're not gonna worry with this kinds of issues. We just have a simple skeleton like this. We just want to work out how many VRs plus 0 there are. So we assume no blocky fish and no 0 segments. Okay. The first thing you want to do is add up all these segments. So in this case, you get +1. You change the sign, so if you have a +1, it becomes -1. If you have -1, it becomes +1, and 0 remains 0. And now you check whether these are the same. And these are the same. And we're going to call this the special case. But this can also be different. In fact, two-thirds of the time it's going to be different. And this is going to be called the generic case. Now, what you're going to be doing next is you're going to be doing 2 to the n divided by 3, where this n is the number of segments. So in this case, it's 3. So if I had just wrote 2 to the 3 divided by 3, you might have gotten confused. So that's 2 to the 3 divided by 3. So this case is 8/3, which is 2.666, blah, 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 blah. This is never going to be an integer, obviously. Notice this is between 2 and 3, and it is closer to 3 and further from 2. So in a special case, you pick the further integer. And in this case, you pick the closer one. So in this case, that would be 2. In this case, that would be 3. Let's actually check our work. Let's actually check that we got the correct answer. So what I'm going to be doing now is I'm going to take this same skeleton, but with all the possible goal numbers. So here we're expecting 2, here we're expecting 3, and here we're expecting 3. And let's see. So in this case, we need to get a -1, so we can either pick this or these two. That's 2. You might wonder whether we're missing one. At the end, we're just going to see that we didn't. So here we can pick nothing. We can pick these two, or we can pick these two. And in this case, we can either pick all 3. We can pick this one or this one. How do we know we haven't missed anything? Well, there are only 8 ways to pick objects out of 3 objects, and because it's 2 to 3. And here we pick 2 and 3 and 3, and 2 plus 3 plus 3 is 8, so we know that anything falls under one of these. So yeah, so this is basically how you do this. So you find out whether in the special case or general case by checking the sum and checking if the opposite of the sum is equal to the goal number or not. And you take 2 to the n, like 2 to the n divided by 3, and you check if in a special case you pick the further integer, otherwise you pick the closer one. And that's how you do this. The rest of the video is going to be aimed at proving this claim. Well, almost. I'm not going to be proving exactly all the details, but I'm going to start. So, so the first thing is that we need to rephrase this into a combinatorial problem, because like this is a combinatorial problem. So basically, we're given a list of integers, a1, a2, up to an, with ai being between plus and minus 1. And we also given a number in z mod 3z. And we ask how many subsets I of 1 through n are there such that the sum for I in I of I is congruent to x modulo 3. And my claim is that this only depends on whether minus the sum from I going from 1 to n of I is congruent to x modulo 3 or not. Yeah, so let's prove this. Proof. This is going to be an induction on n. So let's do the case with n equals 0, which is trivial. The only x equals 0 has a solution. Otherwise, there is exactly one solution. So in the special case, and notice that 0 is equal to minus 0. So yeah, the special case is the case where you get 1, and in the generic case, you get 0. From now on, I'm going to be calling Cn number of VRs in the special case, and Dn number of VRs in the generic case. And our goal will be to prove that Cn and Dn are actually well defined for all n, and also we would like some sort of relation. I don't know, maybe a recurrence formula for Cn, which that's what we're gonna get. We're gonna get a recurrence formula for Cn and Dn. So let's do induction hypothesis. Sorry, induction step. Let's prove the induction step. So we assume the result is valid for n minus 1, and we're gonna prove it for n. So let's say we're in the special case. And then we're going to do the generic case. So let's say we have numbers a1 up through a minus 1 plus and then an, and the goal number is x. Now, we can either pick an or not. Okay. So if we pick an, then we basically are left with a subproblem where we just need to find how many ways you can pick numbers out of the first n minus 1, except that the goal number is x minus an. And is it a special? Are we in the special case or are we in the generic case? So we have to do minus the sum from I equals 1 to n minus 1 vi, and we ask whether this is equal to x minus an. And the answer is no, because if you pull this to the other side, this is supposed to be so basically this is the same thing as asking if an minus a1 minus a2 minus an minus 1 is equal to x mod 3. And the answer is no, because this is x plus an, and an is not equal to 0. So we're in the generic case, which means we have d n minus 1 options. Okay. So the other possibility is that we don't pick an. If we don't, that's not how you spell don't. Then we basically have another subproblem, a1 up to an minus 1, but this time the goal number is x. And again, are we in the generic case or in the special case? Well, we basically removed an, so in this case, our sum is basically x minus an, right? Maybe that would be a mistake actually. Actually, this is x minus an. But okay, it doesn't matter. It's the same. Yeah. Here we actually get that minus a1 minus a2 minus an minus 1. This is actually equal to x plus an. So actually, this is the case where it's plus. That kind of made a sign error. It doesn't matter. We're still in the generic case, which means dn minus 1 options. Which means we just proved that Cn equals to 2 times dn minus 1. So this deals with the special case. So now we need to deal with the generic case. Okay, so again, we have a1 go to an minus 1 an x. And now we can either pick an or not pick an. So in the first case, we have this. And in the second case, we're basically left reducing to this. Right. So now we need to ask whether we are in the generic case or not. Again, we're assuming that the generic case and the special case, the Cn minus 1 and dn minus 1 are well defined, basically. So yeah, what do we do? So we need to check whether minus a1 minus an minus 1. So what is this? Is it equal to x minus an? Well, this is we're basically asking if an minus a1 minus an minus 1 is equal to x, and we don't know actually. And here instead we're asking whether a minus a1 minus a2 minus an minus 1 is equal to x, right? Now what I'm going to be doing is here I'm going to subtract an from both sides, so minus a1 minus minus an minus 1, sorry, minus an, because basically we just added that in, is equal to x minus an. And here instead I'm going to be adding an, and because 2 is going to negative 1 mod 3, this is the same thing as having minus a1. All these are mod 3, by the way. I'm just being lazy with the notation. Right, notice now that because an is not equal to 0, exactly one of these has to be true. Because the difference between these is either plus or minus 1, right? So, yeah, I think you can see that exactly one of these is true. Okay, obviously both of them can be true because an is not 0. And also exactly one has to be the case because there's only 3 possibilities. It's either this difference, the difference between x and these is either plus 1 or minus 1. And because an is either plus 1 or minus 1, then one of these will be the case. Which means you have Cn minus 1 plus Dn minus 1 options. Which means we've proven that Dn equals Cn minus 1 plus Dn minus 1. So yeah, I guess in the claim I should, it depends on n and on whether this is not 3 or not, but yeah. Right, so this is the end of the claim, this is the end of the proof. Now from here, what you can do is you consider our recurrence relations. We have C naught equals 1, D naught equals 0, and Cn equals 2, Dn minus 1, and Dn equals Cn minus 1 plus Dn minus 1. And you can solve these recurrence relations. I'm not going to do this. I already did this, and basically I used generating functions just because they're nice and all. But yeah, after you analyze a little bit and you find out that yeah, you actually do get our result. Also, there's a way. There's actually some elegant way to find out the answer. This is because you can prove by induction that let's see, Cn minus Dn equals minus 1 to the n. Yeah, you can prove this by induction. Which, if you start filling the tables by just doing some value, you realize this is the case very quickly. And also you can prove that Cn plus 2dn is 2 to the n. This is pretty obvious because like we're just finding all the ways to pick stuff, and like this is just a combinatorial identity. This is just saying, a picking is either a solution for a special case or for a general case, and there's 2tn pickings. And from these two, you can see that because the difference is 1, and because they sum to 2 to the n, then you're gonna get something closer to 2 to the n. And in particular, basically because this has like half the weight, this has to be twice as far in a way. I don't know how to explain it, but yeah. So yeah, that should explain it. I guess see you in the next one.